again. I want to report some observations to you this morning having to do with the oxidation of ethylene on silver metal. This is a collaborative effort between a group at Monsanto, John Gleaves and Jerry Ebner, and Alan Salt and myself. And since the time this work was done, John Gleaves has moved to Washington University in St. Louis, and Alan Salt is now at Sandia Laboratories. As many of you probably know from the literature, there are basically two reactive forms of oxygen that have been identified on the surface of silver, and predominantly this work has come from work done on single crystals of silver. These two forms are respectively a dioxygen. Thank you. A dioxygen species to which substantial charge transfer has occurred from the metal to the dioxygen. So here the oxygen-oxygen bond is still intact, and we have shown that this oxygen species on the 110 surface of silver lies flat with the oxygen-oxygen bond vector parallel to the plane of the surface and directed along the close packed direction. So it has a substantial negative charge, if you like, pointing out toward the gas phase. When heated, this species will dissociate at approximately 175 Kelvin, so it is not a very stable species, and accompanying dissociation there is desorption. So basically the characteristic reaction or dissociation desorption temperature of this dioxygen species is 180 Kelvin. This leads to the formation, this dissociative adsorption, leads to the formation of atomic oxygen species, which we have called active oxygen for a variety of their reactivity with different organic substrates. And this active oxygen also is certainly negatively charged and could be thought of as partially ionic. There's, of course, a long and elegant literature on the oxidation of ethylene. It's been discussed mechanistically for quite some time. Here I have a most inadequate and incomplete summary of work. Nonetheless, these are all important contributions. And basically, the message is that there have been differing explanations of the oxidation of ethylene. That is, its oxidation to form ethylene oxide has been attributed either to atomic or to molecular forms of oxygen over the years. And just picking this up in about 1974, a very nice study done by Kilty and Sockler. This is actually a review of that work and the other work in which it's based on the selectivity to form ethylene oxide, the maximum selectivity. It was suggested that only molecularly absorbed oxygen was involved in oxide formation. And through the years that has oscillated around a bit depending on how the current derivative of the pendulum has been. A work by Force and Bell suggested that it was atomically absorbed oxygen that was involved. Then there were single crystal studies done in the 1980s, the mid-80s, by Charlie Campbell and by Richard Lambert and his students. And they differed on the type of oxygen that was involved in the oxidation reaction. Charlie Campbell first asserting that it must be molecular oxygen, Richard Lambert asserting it was atomic oxygen, and so the controversy remained. Then more recently, work by Van Santen and de Groot suggests very strongly the involvement of atomic oxygen in ethylene oxide formation, and that is more or less the point at which we were doing this work to see if we could add more to the understanding of this question. The way in which this study has been made is slightly different than previous studies. In particular, we have used a so-called tap reactor, which in effect is a very rapid micropulse differential reactor. And this type of reactor was developed by Gleaves and Ebner at Monsanto, and has the following general characteristics. The reactants can be pulsed through a small reactor, through a pulse valve, and one can do a variety of things. I certainly don't have time to go into all the possibilities, but one can either pulse reactants simultaneously, that is, you make up a mixture of reactants and pulse them together over a catalyst, or you can pulse them sequentially through two different pulse valves, or you could pulse a reactant while maintaining a steady flow of another reactant across the catalyst. So there are a variety of possibilities, and these pulses can be formed with about a 10 millisecond width. So you can look at very rapid reactions, pulse throttling, pulse delays, on a millisecond time scale, a 10 millisecond time scale. This enables one to look at reactions in a time domain that's much harder to achieve by any other technique. So once the reactants pass through the reactor and products are formed, the products are then sort of skimmed off by a series of differentially pumped chambers, and then finally are detected mass spectrometrically and can be identified by their cracking fractions. So typically, one would inject a pulse at time 0. As I said, this has a very narrow pulse width, and then products emerge from the reactor that are delayed in time due to the finite time for reaction or residence time in the reactor. And also, of course, they have a tail, which is dependent on the characteristic reaction times. So by an analysis of the time lags and the exponential drop here, one can get some information about the reaction kinetics. I'm going to show you some examples of that related to this question of ethylene oxidation. The experiments that I'm reporting to you were done on a silver powder. The silver particles were between 400 and approximately 800 microns in diameter. 0.5, the reactor was loaded with half a gram of this silver powder, and this gave approximately 5 square centimeters of reactive surface area. There are some interesting questions that relate to the initial activation of this material. Perhaps some of you had the opportunity to talk with John Glaze at the poster session the other night. I won't go into those. I'll simply tell you that the initial cleaning and activation here was done by pulsing molecular oxygen over this catalyst at 673 Kelvin. That's a temperature sufficiently high to burn off all the carbon as carbon dioxide. So this treatment was continued until there was no further evidence of carbon on the surface, and the carbon dioxide emission went to 0. This temperature is sufficiently high that any oxygen that would be on the surface would recombine to form dioxygen. And so after this treatment is finished, of course, when it's cooled down, there will be some residual oxygen due to the treatment of the dioxygen. The products, namely ethylene oxide and CO2, were monitored respectively by mass 48 and mass 44. Deuterated ethylene was used in these experiments to avoid overlapping cracking fractions of the products in the mass spectrometer. There was no significant amount of acetaldehyde detectable in our experiments. I'll show you in a moment that the cracking fraction of the oxidized product form in the mass spectrometer is characteristic of ethylene oxide and not acetaldehyde. And in these reactions with this short contact time, there were very low conversions, if you like, per pass, per pulse. This spectrum, this transient evolution of products, is characteristic of a pulse in which both ethylene and oxygen are pulsed together in a 1-to-1 mixture. The temperature of the silver was held at 550 Kelvin. And here you see the evolution of ethylene oxide, as shown by both mass 48 and mass 46, curves A and B, and of CO2, mass 44. And you can see at a glance that the characteristic time for the evolution of the CO2 is longer than that for ethylene oxide. And by looking at the cracking fractions for ethylene oxide, here I show two of them, we could convince ourselves that in fact it's ethylene oxide and not the acetaldehyde. Now, it's possible to using that pulse mixture, 1-to-1 pulse mixture, to vary, and a constant pulse size, to vary the temperature in the reactor and to observe the amount of ethylene oxide formed. And since we're dealing with a reactor in which we only have 1% conversion, no matter how you view the details of the reactor itself, one can extract from that, because the pressures, partial pressures in the reactor stay effectively constant due to the low conversion, one can extract from the amount of product formed as a function of the catalyst temperature characteristic activation energy. Here I show you the Arrhenius plot of the amount of ethylene oxide formed as a function of temperature. You can see that it yields quite a nice Arrhenius plot, linear Arrhenius plot. This gives an activation energy of about 4.5 kilocalories per mole. Now, I don't understand in detail yet the reason for this value. I just simply want to show you that the kinetics of this appear to be reasonably simple for this 1-to-1 mixture. And of course, those of you familiar with ethylene oxidation know that the order of the reaction and the effective activation energies vary all over the map depending on pressure and temperature. So this is not something we have explored in detail. Here I show a number of tap curves for the CO2 formation, again a 1-to-1 mixture varying the temperature of the catalyst. And again you see that the amount changes, although it's very difficult in these experiments because of the breadth of some of these distributions to integrate this very accurately. What I want to show you here is how the tail, the characteristic time for the formation of this product, the CO2 product, changes with temperature. As we go to lower and lower temperatures between 570 and 480 Kelvin, the characteristic time for evolution increases dramatically by going from just a few milliseconds out over to 100 milliseconds. So there's an increase of a factor of 100 approximately in the surface and the characteristic time for CO2 formation. I'll show you in a moment what we believe this long lifetime is due to, but you see very clearly that the kinetics for CO2 formation from this reactor, the rate of CO2 formation is much slower than that for ethylene oxide formation, which essentially stays, the shape of which stays almost constant as a function of reactor temperature. Now, it's known from previous experiments that carbon dioxide interacts with oxygen on silver to form a surface carbonate. That carbonate is a very stable species, and characteristically it decomposes at about 450 Kelvin. So the activation energy for its decomposition is roughly 20 kilocalories. So one suspects that the long residence time for the CO2 may not be due to its intrinsic kinetics of formation, that is, the reaction of surface carbon, let's say, with oxygen, but due to a secondary reaction of the carbon dioxide with the oxygen on the surface. In order to test that, we compared the time evolution of CO2 formed by pulsing CO2 over an oxygen pre-covered silver surface, that is, looking at CO2 plus oxygen to make carbonate, which then reversibly reforms CO2. And that's shown in curve A, that's the jagged one. And here we're comparing that to CO2 formed by a 1-to-1 mixture of ethylene and oxygen, that's the less jagged curve, curve B. And you can see that these curves agree quite well. So we conclude that the surface reactor lifetime of the CO2 is determined by the surface carbonate formation, not by an intrinsic reaction between carbon or ethylene, let's say, to form CO2. And the slight differences here that we see are probably due to the coverage-dependent kinetics of the decomposition kinetics for CO3, which we know to exist. Now I want to talk about a slightly different type of experiment, and this is the so-called tap pump probe experiment. This is something I think that's very unique about this kind of reactor. It allows one to do transient experiments on a very short time scale. For example, if we look at the ethylene oxidation, we can pump in an oxygen pulse. Here actually shown the onset of the valve opening. There's a slight delay due to some lag times in the delivery of oxygen into the reactor. But then there is there is this, and flight times. There is this oxygen pulse that comes through the reactor. Then after that, at some time t, the pulse of ethylene can be sent into the reactor, and one sees the products come out. So we can vary the time delays between these pulses and load the surface with oxygen, and then at varying times send in the ethylene pulse to see what the characteristic time is for the surface species that's giving rise to ethylene oxide. Now, in order to trust the results of such experiments at very short pulse intervals, it's necessary to convince yourself that when you pulse one of the gases, that the residual gas in the delivery line does not affect the size of the pulse of the second one. That as you can imagine, there could be some blocking, some pressure interference, if you like, to the flow of the second pulse that for very short pulse intervals would obscure that. And here's an experiment which is shown in which pulses of krypton have been injected after an oxygen pulse, and these pulses of krypton shown here and here have been delayed substantially, or differ substantially in the delay time. They're equal pulses of equal magnitude, and what I show on the bottom scale is that the size of the pulse then that comes out of the reactor is unaffected by the delay time. So we don't have any spurious effects of the magnitude of the pulses introduced simply by pulse interference. Now, before I show you, well, let me show you one effect here that's interesting and which we don't completely understand at this point. This is a pulse probe experiment where oxygen has been pulsed in to load up the catalyst, and then ethylene follows at varying times, and the ethylene pulses are equal in size. And here we have the amount of ethylene oxide formed at 523 Kelvin as a function of the pulse delay. What's interesting about this is that for very short pulse intervals, there seems to be a process here which retards the formation of ethylene oxide. And this process has a time which is about the order of a tenth of a second. Now, we don't understand the details of this. John Gleaves is currently investigating this further. It may have to do with reorganization of oxygen in the surface and subsurface layers. It's known that subsurface oxygen is important for the formation of ethylene oxide. And since we're stripping off the oxygen in the pulses as we go through, at very short time intervals, it may be necessary for there to be a rearrangement, if you like, transfer of oxygen into the subsurface layer in order to produce ethylene oxide with high efficiency. It could also be that there are certain residual surface species, such as surface carbonate, which retard the formation of ethylene oxide initially, and then which after a longer delay time are washed out of the system and don't have any further effect. But I think it's interesting at least to point out that these kinds of effects can be observed in this type of reactor because of the possibility of injecting these sequential pulses on such short time scales. Now let's return to the major question, and that is whether we can distinguish between the involvement of molecular oxygen or atomic oxygen in the reaction to form ethylene oxide. The rate constants for desorption or conversion of molecular oxygen into atomic oxygen have been investigated, as well as have the rate constant for associative desorption, recombinative desorption of atomic oxygen. And so we can estimate reasonably well the lifetime of a dioxygen species on the surface or the lifetime of the atomic oxygen. And here are tabulated some estimates of those values at various temperatures on the silver surface. All of these values, these half-lives, have been taken from data on silver 110, for which the kinetics have been most accurately determined. And you can imagine that there may be slight differences on other crystallographic planes. There may be slight differences due to the presence of defects on the surface, but at the order of magnitude, these estimates should be reasonably accurate. Well, the point is this. The lifetime in seconds for atomic oxygen at these temperatures vary from the order of seconds to the order of, let's say, minutes. The lifetime of the molecular oxygen on the surface, depending on which rate constant one takes, differ substantially for these two rate constants, but the most conservative value of the lifetime for the molecular oxygen is on the order of 10 to the minus 4 seconds. It has to be a very short-lived species at 550 Kelvin. Because, as I said, its characteristic temperature for reaction is 180 Kelvin, so it cannot have a long lifetime. So you can imagine an experiment in which you load up the surface with oxygen by a pulse, and then you delay the pulse time with the ethylene, and observe the decrease, the transient decrease in the amount of ethylene oxide formed. If molecular oxygen is the surface species responsible for ethylene oxide formation, then there should be an instantaneous decrease between the pulses. In other words, effectively after 10 to the minus 3 seconds, one should no longer see any significant amount of ethylene oxide. If atomic oxygen is active for the formation of ethylene oxygen, then the characteristic decay time should be the order of let's say, 10 seconds to a minute. So we did that experiment, and let's just look at the dark skyscrapers. These skyscrapers are rectangular representations of the actual pulse coming out of the reactor. And what we see here is that initially, after we put the oxygen in at 550 Kelvin, and then we begin to pulse ethylene, we see initially, let's say, normalized to 10, that the first ethylene oxide pulse comes out with magnitude 10. If we just scan down here to something approximately half of the size of the initial peak, you see that the characteristic time for the characteristic half-life is approximately one second. It's certainly not 10 to the minus 3 seconds. That is, it's of the order of magnitude of the time we estimate for the lifetime of the surface atomic oxygen species. So what we believe this shows is that atomic oxygen is definitely participating in the formation of the ethylene oxide species, and that in these experiments there is no molecular oxygen around basically to interact in that process because of the time scale. So I'd like to conclude this part, and how am I doing for time?
About 5 minutes.
And 5 minutes, all right. And then if I have 5 minutes, I'd like to show you something that thickens the soup. So my conclusion, or our conclusion here, is that under conditions studied, that oxidation of ethylene proceeds via reaction of ethylene with dissociatively absorbed oxygen, that clearly establishes that dissociatively absorbed oxygen participates in this reaction and is in perfect agreement with the experiment of Van Santen and co-workers. I'd like to show you some other results that I think also supports this, but does thicken the plot a bit. That is, we haven't shown that dioxygen does not do this. We just think it's very implausible based on its lifetime, the concentrations you could have in the steady state, even under steady state catalytic conditions, that it could. But we have been looking at reactions of dioxygen. And to my knowledge, there have been no demonstrations of reactivity of dioxygen on metal surfaces prior to this. But one might expect that this should react. After all, dioxygen is a reactive species in bioorganic systems, in organometallic complexes, and so one would expect to have a reactivity of dioxygen on surfaces, although it might be meager. Here I show you a charge contour drawing of dioxygen, the two gray circles, adsorbed on silver 110. This is the surface plane, surface atoms, topmost surface atoms in that plane. This is the subsurface plane. What this shows, I don't want to go into the details here, but what this shows is the net charge difference between molecular oxygen and the surface, no chemical interaction at all, and then the molecular oxygen or dioxygen surface interaction when you turn on bonding. What happens is, this is the excess negative charge that one sees. What happens is charge is transferred into the pi star orbitals of the dioxygen, and you can see gives this a high electron density the oxygen atoms, if you like, making up the dioxygen, a high electron density, and if you like, ears pointing out toward the gas phase. So you might expect that with this high charge density sticking out toward the gas phase, that you could get reactions with strong pi acids, good electron acceptors. Now, ethylene is not a good electron acceptor. So this is, again, consistent with a low reactivity of ethylene with dioxygen, but we wanted to see whether or not it was possible to react the species with good pi acids. And there are two very strong electron acceptors because of their low-lying pi star orbitals, that is CO and SO2, and we looked to see if we could get reaction with CO to form either CO2 or carbonate, depending on whether it adds in a concerted fashion. You could get carbonate if it added by, if you like, withdrawing an oxide ion from the O2, it could make CO2 and leave behind an oxygen atom, which would then react to make carbonate together. And by analogy, SO2, if it reacted in a concerted fashion, would make SO4, or it could pull off an oxygen ion to make SO3 and leave behind some more oxygen. Let's first look at the result with carbon monoxide. And I show here on the bottom the vibrational spectrum for O2 itself, and superimposed on that what you'd expect for carbon monoxide if the two adsorbed without reaction. So we're going to look at a vibrational spectrum. If they don't react, we expect to see this. What is seen is shown here. All the blue, green, and yellow peaks are the result of, except the red one is not. The blue and green peaks are the result of reaction to form carbonate and CO2. So clearly there is a facile reaction. This is occurring at 95 degrees Kelvin. The barrier has to be infinitesimal. There's a facile reaction with the dioxygen by this good electron acceptor to form surface carbonate and CO2. Similarly, for SO2, this is the spectrum one for SO2 adsorbed on the clean surface. And when this is added to the surface dioxygen, this is what we see. And the red peaks are the result of vibrational modes of SO3, surface sulfite. So there's clearly a reaction between the SO2 and the surface dioxygen to, if you like, abstract an oxide anion, O minus, O partial minus, and leave behind an oxygen atom. So it's clear that, the punchline here is it's clear that reactions do take place between dioxygen and gas phase species. This reaction doesn't take place under these conditions for ethylene, and our understanding of that is that ethylene has such a poor electron affinity, a negative electron affinity, that it can't do that kind of reaction. And so again, we believe that this reaction, the ethylene oxidation reaction, is primarily caused by atomic oxygen. Thank you very much.
Thank you very much. May I ask a question? If you use the data from your pulse reactor to make a prediction for the steady state under continuous flow conditions, are you saying that, at least in the absence of chlorine, the steady state surface coverage is mainly carbonate?
That's an excellent question. We haven't attempted to do that. And of course, it depends on what steady state conditions you pick. And one of the things I tried to stay away from was the details of the odor and the activation energies and those kinds of details. I think this is much too preliminary to let us be that bold.
Okay. Dr. Fischer?
In the case of the, by the way, in the case of the molecular reactions of oxygen, Matsushima reported CO2 formation with dioxygen and CO, but you could argue maybe that it's happening as the oxygen dissociates.
I know for a fact that reaction happens after the oxygen is dissociated. So that's why I was careful about choosing the words.
In the rate constants that you used for the dioxygen, were those for absorption, or is that somehow the rate constant for the lifetime of this parallel bound O2 state on the surface. I mean, that's the one maybe that you're most interested in. Its lifetime as opposed to the other number.
Yes, the lifetime I used is the lifetime of this parallel bound species. You can use Charlie Campbell's results for O2 desorption from silver 111 for where you don't have a facile dissociation of the molecular oxygen species, and on that basis the lifetime should be even shorter.
The last question for Professor van Santen.
I very much appreciate your elegant experiments. Question remains about the oxygen richness or poorness of the silver surface. Am I right to conclude from that in most of your cases your silver surface indeed is oxygen rich?
Yes, you are. In other words, the pulses, we don't know exactly what the coverage is, but the pulses, I'd say a rough estimate would give us at least 1/10 of a monolayer of oxygen. That's a very rough guess, and we don't know quantitatively yet what those are.
The low activation energy you find for the oxidation, could that be due to the fact that you already have your oxygen on the surface and it's just a reaction of the ethylene with the dissociated oxygen that's already there, so that you do not have to dissociate the oxygen from the gas?
That's right. There would be no expression in the overall rate equation which involved any kind of oxygen dissociation on the surface, and it's known, of course, that there is a barrier for dissociation of oxygen, which could be a few kilocalories. Yeah, that's a good possibility.
Okay, thank you very much for this lecture.